This is the second of the portion series talks we're having this year, continuing the theme of refurbishment, which we did last time, but this time focusing more on Passivhaus and particularly looking at the cost efficiency of refurbishment with Passivhaus, or EnerPHit as it perhaps is more accurately named. I think the new build aspect of Passivhaus is pretty well established now, with thousands of projects built worldwide, and it's almost becoming quite mainstream. And I believe in this country there are some quite large developments now being considered at Passivhaus standard. So it's all looking very encouraging. But in terms of refurbishments, we seem to have a lot more to do, and I guess the technical challenges associated with refurbishments are slowing that rate of work down. The government has set some quite serious targets, and I guess we're probably bored of hearing that by 2050 we've got to get to 80% less carbon emissions than we're currently doing. And it's interesting to see that 70% of the building stock in 2050, they estimate, will still be existing buildings, or buildings which predate 2005. So it's quite a mammoth challenge that we've set ourselves. Low energy refurb has a key role to play in getting us down to those targets. The question is Passivhaus is Passivhaus the right way to do it? We can aspire to it, and we can get close to it, and maybe that's the answer without actually getting relevant certificates. We've got some highly qualified speakers with us this evening who are going to talk about that subject. The format for the evening is for each speaker to talk for about 15 minutes, and then we're going to have a discussion at the end of the debate. So if you could hold back any questions until the end, that would be very good. The first speaker this evening is Maiia Guermanova from Buro Architects, who is going to talk about their Maiia Community Centre. Buro Architects need little introduction. Justin has... I guess we put my glasses on here, sorry. One of the foremost Passivhaus firms in the UK. Justin is a member of numerous professional Passivhaus committees and organisation, and is a founder member of the Passivhaus Trust in the UK. And we're very pleased that Justin is here tonight as well. Maiia has done a lot of work on the Maiia Community Centre, which I'm sure you know is a winner of many awards, more than I can list here. And interesting to see that it actually achieved the Passivhaus standard higher than the EnerPHit standard, which is a real achievement, I think. So Maiia, over to you.
Hello everybody. So just as a little introduction, I've been working in Buro Architects for about 10 months, and on a range of projects, and although unfortunately I didn't get a chance to work on the Maiia Community Centre myself, I was involved in sort of reports to do with monitoring of the centre. We were commissioned by Technology Strategy Board to monitor the Maiia Community Centre for 2 years, and I mean, we have some fantastic results. But predominantly on this project I work on the cost comparison. I concentrated on comparing Passivhaus refurbishment, which is non-domestic, to the sort of standard refurbishment to building regulations, and this is what I'm going to speak to you about. Okay. Okay, so this is the community centre report. we got to it. It was uninsulated, fairly derelict, and a little bit depressing looking building, and basically comprised of skin of block brickwork. The next image sort of gives you an idea what it looked like inside. Pretty gloomy. And so this what happened after Buro Architects refurbished the building. Just to sort of clarify a little bit, it was retrofitted to Passivhaus standards, as was already mentioned, which is a lot higher than EnerPHit standard, and sort of particularly it's to do with the obviously the U values and the air tightness of the building. So the air tightness of this building is 0.42, which to achieve Passivhaus you need 0.6. So the building actually performs brilliantly. So this is the view from the outside. It's sort of south-facing facade. We've increased the size of the building by extending, sort of excavating and extending the basement. So now there's 35% extra office area, which obviously brings profit to the centre. And it has a wonderful sort of open plan reception area. Sort of just to go through some of the points, when the building was designed, we were trying to achieve 90% less energy use, reorientating sort of the building so that it's more offices face south, obviously opening up the basement as I mentioned earlier, and for those of you who are more technically minded, you might be interested in services strategy. The building has a ground source heat pump and a separate heat recovery ventilation system, which is quite cleverly can be switched off in the summertime when you can utilise natural ventilation. The main hall is also fitted with CO2 sensors, so you have obviously more air coming in when it's needed. This is our certificate. As you can see, achieves Passivhaus standard. It uses renewables. It has an array of PVs on the roof and solar thermals, obviously as well as the ground source heat pump I mentioned earlier. This is the image taken last winter. You can see with infrared photo imaging camera, and you can see the building performs so much better than the estate around it. It's actually quite a deprived area, and we see this building as a gem, which attracts the community, and hopefully gives you an idea what happens inside. Incidentally, our office actually moved to the basement, so we get to enjoy the building as well. And we meet all of these wonderful characters, the local sort of ladies that come and play bingo every week, and just the sort of people respond really well to the sort of the comforts of the building. In the past, we've heard people mention that they actually weren't able, when they were playing bingo, they had to keep the jackets on at all times, and now they actually get to enjoy it fully. Sort of the kitchen, run by the ladies, on sort of various occasions. It's a really, really cheerful place to be in and work in. Sort of back to the monitoring. We in the first winter that we monitored, although I have to say, we have to note that the basement was not fully occupied at the time when this was taking place, which is a bit of a disadvantage in a way. But on the other hand, the data you see here, which shows the existing and the use of the building in red, you can see how high it was compared to what is actually used now, as actually monitored and recorded by us on a weekly basis. We have submetering, so we have every separate sort of unit in the system is recorded separately, and and you can see later the graph that shows that. One thing I wanted to add, as at the time we did the monitoring, we did our PV sort of system included all of its included the energy that is always selling back to the grid. Going back into the grid. So actually, the blue element should be reduced by about 9%, because we fitted the submeter and for 1 month now, and that's what it's sort of the indication is. So it's even better than it's showing, which is great. And the PHPP design predictions, which I'm not sure whether you're aware, but to design a passive house, we have to run a software PHPP, which does all the calculations, and it's a fairly conservative software, and you can see that actually the actual energy use in the building is a lot less than we predicted when we designed the building. This is sort of the breaking of the energy use, and the peak is an unfortunate incident of the old ladies having a Christmas party. They like being warm, so they put the thermostat full on and they left the building for a week. So, but having that, you could see that the building is still performing wonderfully. Costs, and this is where I came in. So my task was to answer the question, which is asked fairly regularly at various talks, is how much extra does a passive house cost? And so to do this exercise, we sort of decided to not just compare the building as we designed it, which had the ground source heat pump and the solar installations, but to compare it to the building regulations. We decided to kind of compare it in a more fair way. If we were to design a passive house and install a simple sort of gas boiler system in it, which is the likelihood, if the building was retrofitted to building regulation standards, that's what would have happened. So that's why you see so many columns in my chart. Just sort of to run through it, we compared the before refurbishment, the building regulations, with the gas boiler system used for heating, the passive house using the gas boiler so that it's comparable to the building's regulations. We passive house using the heat pump and great. Okay, the passive house using the PV installations. And to run quickly through it, we looked at the old energy bills for 2009. And obviously we had a set of monitoring data, which you've seen already. And in this cost exercise, we used a cost plan and the PHPP documents created for various scenarios. And this is the sort of the monthly, annual energy consumption. And before refurbishment, you can see it was 8,500, which is substantial amount for a sort of community centre. And what we're predicting, because we don't have the full set of bills at the moment, using the PHPP data we have, is sort of just over 1,000, which is quite a big difference. And this is obviously taken into account the PVs on the roof, which are feeding the electricity back into the building. So if we didn't have the PVs, this would be sort of the cost of running the building, which is 3,000 or just under 3,000, depending whether we use the ground source heat pump or the gas boiler. And the next slide is similar situation. The CO2 emissions very high for existing building and substantially lower for the passive house. So the next thing we did is sat down with our QS and ran through every stage using a cost plan and decided, taken the elements that would change, particularly items like insulation, triple glazed windows were changed to double glazing and so forth. And based on that analysis, we came up with this wonderful figure. Passive house with a gas boiler only costs 3% more, which is came as a bit of a surprise to quite a lot of people in our office as well. And I guess it's really good news for the industry. The actual building, because we have such expensive systems installed in it, such as ground source heat pump, was nearly 8% more expensive. But taking into account all the grants we got for installation of those systems, again it brings the cost down to just under 4%. So either way, it's worth it. Thank you.
Thank you, Hannah. Okay, next speaker is Mark Dowson from Buro Happold, who is a research engineer in their sustainability and building physics unit. Has recently completed a 4-year engineering doctorate with Buro Happold and Renewable University, focusing on retrofitting, product development and also aerogel insulation. We're currently working with Mark on the Arrett building in Cambridge, and if you came to our last talk you would have heard Mark, sorry, you wouldn't have heard Mark. You'd have heard Alistair, explaining about the sustainability framework which they're developing for that project. As part of the government's funded competition launched by the TSB 3 or 4 years ago, Mark was part of a team that refurbished an end of terrace 1960s dwelling on the Thamesmead Estate, and Mark is going to tell us what happened.
Right, so the title of the presentation today is 10 lessons learned from a near Passivhaus whole house retrofit. So we aimed for Passivhaus but didn't quite achieve it, so I'll tell you the story. So presentation overview, pretty much covered my background I think, so I'll dive straight into a retrofit for the future case study I was involved with, and also talk in a bit of detail about some innovation we did on the project with aerogel insulation. Then I'll quickly run through the lessons learned from the whole project and some of the monitoring results we're getting out. So as I say, background, just a bit of my, well, last Wednesday actually I had my viva for my engineering doctorate. I passed it, so I'm quite happy about that. So retrofit for the future. For those who don't know, it's a competition launched by the Technology Strategy Board back in I think 2008 actually. And the competition basically refurbished about 86 houses across the UK, bringing teams together, and each team was offered £150,000 funding. And the overall aim of the competition for each of the teams was to cut the CO2 emissions from a low-rise social house by 80%. So this is the house that our team retrofitted, our team consisting of Maiia Architects, Martin Arnold Associates, we've also got Jim Martin today who's going to be talking after me, Gallia's Housing Association, Axis Europe Contractors and BH. So the house was a 1960s end terrace in the Thamesmead Estate in South East London. Thamesmead Estate, for those who don't know, was featured in the film Clockwork Orange. It's got quite a lot of history behind it. There's like a few hundred pretty much identical houses on this estate, all kind of uninsulated concrete walls, pre-insulated concrete walls, but only about 50mm of insulation. A mixture of kind of single and double glazed windows, a mishmash really. But kind of back when it was originally designed, all of these houses had a district heating network kind of built within them, but kind of since the energy crisis back in the 70s, that whole district heating network was made redundant, and ever since then there's kind of been moisture related problems and heating problems in a lot of these houses. So they're quite a challenge in front of us really. So before we kind of started any on-site works, we did a fabric assessment of the building. This image here basically shows a section through the existing walls. That's the concrete wall with 50mm of insulation in it. It's basically kind of a panelised construction system, so everything kind of slotted into place. So quite a lot of potential air leakage paths, I guess, we found at the end of the project. This was probably one of the main reasons why we struggled to achieve Passivhaus, just dealing with all the kind of nooks and crannies of air tightness in this type of construction. So the air tightness that we measured on site before we started was 9.1. So that's quite good actually, because building regulations is about 10. But we still had quite a way to go to get down to the Passivhaus requirements. We also did some in situ U value testing on site, so this is when you measure the actual U value of any kind of element. So we did it for one of the balancing system walls, an overhanging section of the roof, and also on the floor. And what we found was that basically the predicted U values matched quite well with the measurements. And for those who don't know, to measure an in situ U value, you basically stick a heat flux sensor onto a wall and measure the air temperature internally and also externally, and then the U value is calculated from the heat flux divided by the temperature difference over a period of time, say a week of testing. So it's quite a good idea actually to kind of do that before we start refurbishment. It gives you kind of a bit more confidence in terms of the values you can put forward into your thermal modelling, for example. So this was kind of the baseline thermal model that we did, just to calculate baseline CO2 emissions and kind of aggregate the kind of end uses in the house. So our baseline was over 100 kilograms of CO2 per metre squared, and the kind of target set by the TSB was to get down to 17. And flex heating was obviously the main kind of source of energy consumption in the dwelling. Our retrofit strategy, after kind of a lot of deliberation and lots of long meetings in the design team, we kind of decided to go for the Passivhaus standard. So high levels of air tightness, 0.6 to 1 air changes. We decided to externally insulate the property because the property wasn't listed, and we thought we had the opportunity to really transform the external appearance of our dwelling. So for Passivhaus you kind of need to aim for a U value of about 0.1, so 300 mm of insulation. Triple glazed windows with quite high solar G values. External doors had to be super insulated to a U value of 0.8. Then all the kind of standard stuff really, thermal bridge-free design, mechanical ventilation, heat recovery. We also had PVs on the roof and solar thermal. For the peak kind of winter demand we had a gas condensing boiler. So this was just some modelling I did to kind of look at how to achieve that kind of 80% reduction just in theory before we started. So we kind of started with our baseline, and then kind of sequentially as you add all the measures like the insulation, you get a big drop, probably cutting about, I don't know, over 50% of the CO2 emissions, and then actually kind of add in more things like the triple glazing and the MVHR. The benefit kind of reduces as you kind of keep trying to squeeze more out of the building. By going through that process we got down to 19, which was just above the target, but with the PV panels we managed to slip below to the target. We got 14 there, but just in theory, remember. So this is a section through the house that the architects drew using Revit. You probably wouldn't normally go to that level of detail on whole house refurbishment, domestic anyway. But just because of the kind of research nature of the project and the vested interest from the architects, they went to quite kind of high levels of detail to kind of make sure we had a thermal bridge-free design kind of after refurbishment. So we had a 4-bedroom house before, and then they converted it into a 6-bedroom house. So the original property had a kind of ground floor garage, walkway. This is where the entrance was, and it's now kind of got a large kitchen diner on the ground floor, large living room extended. The garage has been turned into a plant room area. The roof has been flattened to allow kind of renewable technology to be put there. And as I mentioned, we were quite interested in doing some innovation with aerogel on this project. I've got some samples here actually which we can pass around maybe if we go one way. So aerogel, for those who don't know, it's a super insulation material with the best insulating properties of any solid. It comes in quite a few forms. You've got translucent granules, which is this panel being passed around now, and those granules can be filled inside kind of plastic or glass panels. And you also get opaque insulating blankets, which are the smaller samples, which is kind of fabrics with kind of aerogel particles embedded within them. So in our project, and my kind of vested interest in the doctorate, we were quite keen to kind of pursue what kind of applications with aerogel we could install into this project. So one of the solutions that we looked for was putting it into the ground floor. So we had a concrete slab and a limited floor-to-ceiling height, and we wanted to achieve a passive house U-value for the ground floor. So in certain areas here and here we had plenty of space for kind of polyurethane insulation, but in one area we only had 80 mil of space available. So by incorporating aerogel into the design, we were able to achieve a passive house U-value through that. It turned out to be quite expensive though in that application. The next application we did was in an external plant room door. So we had our front door, which was the Passive House certified door, costing about £4.5 grand, I think it was. And then besides that, we also had a double leaf external plant room door. And we thought we don't want to be spending £4.5 grand again. We need to come up with some alternative solution. So we worked with Proctor Groups in Scotland who basically sell the space load insulation, the blankets that I was passing around. And they built us a custom-made plant room door with kind of 10 mil of wood and then 3 10 mil space load blankets embedded within it. And I'll tell you later on how that performed, but in cost terms, that kind of double leaf door being larger than the Passive House door only came in at 1,800 quid, so it made a small cost saving there that we were, well, compared to £4.5 grand, yeah. So we were quite pleased about that. The main kind of innovation on this project was looking at preheating the mechanical ventilation system using a solar air collector on the south facades. So basically what we're doing is we're taking air from our wet rooms in the house, so the kitchens and the bathroom, and we're feeding that into a cavity of a solar air collector on the outside of the building, so that air, before it enters the MVHR to preheat the incoming supply air, it's gaining kind of additional energy from the sun kind of passively in order to kind of gain higher temperatures. So the solar air collector, which lets the solar energy in, it traps it and it uses it in the house. And now I'll just quickly run through some of the on-site photos from the retrofit process. I mean, I guess the first thing to note is that working with Axis on this project, they had no experience working with passive house projects before, so it was really quite key to do the kind of air tightness briefings at the beginning, because they're going to be working with a lot of kind of membranes and tapes and sleeves for surfaces penetrations, which they'd never really, I don't think, used before. So those at the top were kind of the main kind of products that we used. This photo shows an airtight sleeve on the boiler flue, and this shows the roof membrane being installed before the insulation was put on top. Here's a photo of the external cladding going up. Interestingly, this photo here, these kind of blocks here, that's all the insulation stacked up before it went on the house, and I'm probably about that big, so there's about 3 times the amount of insulation required, so you probably need quite a big garden if you're going for external insulation to passive house standards. And on the right shows the cladding going up, and also the startings of this solar air collector being built. Triple glazing, this photo basically shows the extended living room area with a large area of glazing. This photo shows some of the tapes put on the edge of a triple glazed window. All our glazing was supplied from Nordan. And then on the roof we had 10 PV panels and 1 solar thermal collector preheating about 40% of domestic hot water supply. All of these panels were ballasted to the roof using an aluminium framing system, which was then ballasted with concrete slabs, because it was really important that we didn't penetrate through the roof insulation line and the air tightness barrier. So it took us quite a long time to actually find a suitable way of doing that. This is a view inside the plant room, so we had our mechanical ventilation system, lots of monitoring equipment at the back as well. With the MVHR, it's, I guess, important to note that it had a summer bypass function specified with it, which basically means that it has an ability to detect the outside air temperature, and if the outside air temperature exceeds 20 degrees, so in summertime, there's going to be no preheating of the fresh air being sent to the house. So it's a mechanism to try and mitigate overheating in the summertime. I'll just show you some photos of the solar air collector being installed. So it's a 6 metre wide system, about 1 metre high. It's got an inlet duct and also an outlet duct, and it's got a timber frame which was then insulated at the back with some reflective insulation, and around the outside of the frame is some mineral wool to act as a fire break, because this is kind of a heat generating technology, so we didn't want to risk it causing any fire issues on the property. Inside the house we had insulating ducts rising from the plant room, going into the collector and coming back down into the MVHR. Inside the cavity we have black perforated metal sheets to kind of take the energy from the sun and then heat up the air inside the cavity. And then we slotted in the aerogel covers at the front to kind of seal the system. So the reason why we're basically using aerogel in this application is because the insulation properties are much better than just a sheet of glass, even double glazing. But you do get slightly lower solar transmission, but overall the efficiency works out better than just having a glazed panel. We also installed monitoring sensors inside the cavity to measure temperature and humidity at 8 different points. And on the roof we also had a solar radiation sensor. So this effectively would allow us to validate all of our efficiency calculations for the system. This is a photo of the seal collector when finished. And the house from ground floor. So the bright yellow / green colour was chosen by FBM Architects, and as well as that, these kind of strips here are kind of 50mm aluminium extrusions on the outside, and the reasoning behind that for the architect was really because if you're going to be externally insulating a lot of properties in the UK, then you don't want to risk losing the character of our housing stock. And the idea of these fins in particular was that as the sun passes over the sky in the day, it will cast shadows at different lengths across the building. So if you look at it at any kind of time in the day, it will look different. Some more photos of the house. So there's quite a lot of glazing on this elevation, and we've got a fully glazed kitchen on the ground floor. And there's that plant room door I mentioned next to the front room door. Just do a bit of thermal imaging commentary. So this was thermal images taken before the retrofit. I mean, basically, all that's to say it's all red, and you can see our kind of building here, and then a building in the background, and there's no real differentiation between the two. These panels at the top here were asbestos panels, and they kind of performed quite bad, but really no worse for the rest of the building. It was all quite bad. And then here's some photos after the retrofit. So you see kind of quite significant improvement in the main fabric, but maybe there's some issues with the way the glazing was installed. Let's see. In terms of Passivhaus certification, this is kind of the crux of the lessons learned that I wanted to talk about actually. It was a long back and forth process with the contractors, measuring the air tightness, doing smoke tests and doing corrective works essentially. So a lot of the measures that were specified, like an airtight roof membrane, sleeves and all the surfaces penetrations, a lot of them weren't actually installed first time around, despite us kind of being on site every couple of weeks with the contractors doing reviews and asking them has it been done. So a lot of kind of abortive works had to be done, and ultimately this was kind of the downfall of the project, not achieving the air tightness levels required. So this basically shows the Passivhaus calculations. So if we had an air tightness test of 0.6, we would have achieved 23 kilowatt hours per metre square per year, which is below the kind of refurb target of 25. We would have also achieved it if we had got 1, but we actually only achieved 3.6 on site. But I mean, 32 kilowatt hours per metre squared. I was speaking to someone earlier and they said that was quite good actually, so I think we can be proud of it really. We did some inspection on the outside of the building to see if we can kind of isolate where the main kind of air leakage problems were, and we really kind of felt some of the main problems, apart from the kind of products being ordered off spec, was also maybe the way the partition wall was treated between our property and the next door neighbour, particularly kind of where the floor slab met in the middle of the building, because we can kind of see there wasn't a clean line of where our property kind of starts and starts. That's probably where some of the main issues arose. 10 lessons learned that we found. I mean, Jim's going to give a completely different perspective on a lot of this stuff maybe a bit more in detail on costs and things, but 10 lessons learned. So there should be an understanding at the outset that Passivhaus cannot and maybe should not be applied to all retrofit projects due to the disruption and technical challenge. Before adopting Passivhaus, the project team should be fully trained on the work methodologies required to achieve certification, specifically with regard to air tightness. Thirdly, Passivhaus projects greatly benefit from the services of a contractor with specialist expertise, as the process requires a step change in construction quality. It's a very good idea to smoke test before retrofit work commences, as this will identify the key elements to be addressed, and we found by going through an external insulation air tightness strategy that party walls can be a particular problem. To avoid any remedial works, all air tightness tapes and barriers and services penetrations must be properly sequenced before the glazing and insulation is installed. These all sound like obvious things, really. Next, allow plenty of time for specialist items such as triple glazing, external doors and the MVHR, since the UK market for these products is currently underdeveloped. It can take up to 6 weeks to get any of these items in, so you just need to plan for it. One that was quite important for us was make sure the contractors don't cover up any of the materials and joints forming the airtight barrier until the installation quality has been inspected and the airtightness has been verified. And as a result of this, maybe try and agree some contractual hold points for airtightness and smoke testing to take place after all significant fabric upgrades, and review the programme and costs at each stage of the project. It's important to have an airtightness champion on site full-time or part-time that understands and can predict the problems associated with refurbishment. And proper on-site training and inductions of all subcontractor site staff is essential before they're allowed on site, to avoid any uncertainty that it's a Passivhaus being worked on and there's certain rules that need to be followed. So don't forget any of those lessons. Here's a couple of more kind of experimental monitoring that we did. So this shows a thermal image of our aerogel door besides the Passivhaus door. And you can see the Passivhaus door looks a lot brighter than our space therm door on the thermal image, which basically shows that our aerogel door performed thermally better than the Passivhaus door. There's quite a bit of leakage on the actual kind of the joints in the door, so maybe the product in terms of air tightness could have been improved, but in terms of the U value, there was an improvement. We actually did some in situ U value testing of the product as well, and the centre of blade U value, so excluding all the frame, was actually 0.38, so a lot lower than the 0.8 of the door. Inside our solar air collector preheating the MVHR, this graph basically shows 7 days worth of testing in October of last year. The big orange bars are basically showing the amount of sunshine we got, so these are all kind of sunny days during a week in October, and the external temperature was like 5 to 15 degrees outside. And basically we had air entering into the collector, this dotted blue line, between say 20 and 25 during the daytime in the inlet, and then in the outlet of the collector the air was peaking at around 45 degrees. And that's all going on inside the collector. This was what was going on inside the house. So with that air at 45 degrees then passing down into the plant room, indirectly mixing with fresh air being supplied to the house, so that fresh air being preheated by the 45 degree air was getting preheated to 25 to 30 degrees, which is then being directly fed to the house. And all the while it was kind of 5 to 15 outside, the internal temperatures in the house with no occupancy at the time was about 21 to 22 degrees, quite stable actually, with no additional heating going on. We've been doing long-term monitoring as well in the dwelling, mainly of temperatures because occupants only moved in June of this year, so we don't really have any long-term gas or electricity data yet. But in terms of external temperature, this basically shows the average external temperatures that we had. So the average outside temperature was about 10 degrees over the whole data set. Our average outlet temperature in the collector was 40 degrees, and the average temperature of the air being supplied to the house was 28. And inside the living room, the average temperature inside the house was 20 degrees across the whole of the last 11 months. And this figure is basically the average of the maximum, so I'll just tell you what the maximum was. So we had internal temperatures of 26.8 degrees measured at the time when it was probably like 30 degrees outside. They were kind of the peak outside temperatures that we had in the summertime. We received a fair bit of trade press on this article in the June issue of the City magazine, and also still in internal and architecture publications. But that's where I'll stop really. Hand over to Jim.
Okay.
I'll just very briefly introduce Jim, who's a founding partner of Martin Arnold Associates, and Jim has a wide range of projects under its belt, residential, leisure, and also education. So, I'll leave you to
Thanks very much. Thank you. Good evening, everyone. Love to see such a big crowd. Sustainable, blah, all of that stuff. I won't go through all of this because Mark has covered it a lot better than me. Very, very difficult with an expert in the room, you know. So what can we do about it, blah, you know, all of this sort of stuff. How can the measures be implemented? Individual, local, national, international. Now, I might come back to this because I think it's quite an interesting issue. But this is what I sort of, you know, I'm here in the, you know, sort of sake of balance, as it were. And, you know, from all of the stuff that I've done, what I know is that you can make the most energy saving in a building by educating the tenant. Don't do anything. I know that's bad news for a group of construction professionals, but actually educating the tenant is the way you save most energy. Yeah. Then, if you can make the building fabric as efficient as possible, make systems. This moves into sort of passive house. And you know, last of all, you know, much as I love Mark's aerogel system because it is fantastic, it's probably just the icing on the cake, as it were. This really is the costs is my thing. I'm a chartered building surveyor, but costs have for many years been my issue on buildings, and this is it. This is why passive house cannot work. Yeah, it's called the law of diminishing returns. Yeah, the more you pay, the less you get. Yeah, so while you can do tons and tons and tons of stuff relatively at a low price, educate the tenant. Insulate the building, get the systems in the building working better. You know, you can do that at a relatively low price. Once you start adding aerogel technology, once you start adding solar thermal collectors, photovoltaic cells, ground source heat pumps, your cost goes through the roof, and your carbon saving is relatively small. Now, this is great if, you know, you're a middle class person and you want to get on grand design. This is lovely because it doesn't really matter. But if you're dealing with Thamesmead, which, just to correct Mark, there's not 400, there's 6,000 properties in Thamesmead, similar to the one that we worked on, you can see that it is absolutely, it's £1 billion issue. Yeah. So while the costs, I can tell you specifically, £336,000, 55 Wolvercote Road took to refurbish, which is ludicrously expensive. But if you roll that out across the stock in the nation, yeah, you're going to see we're talking billions and billions and billions and billions of pounds. This is why passive house can never work. Work on a small scale, work on an individual project, absolutely no problem with that at all. But we cannot roll it out across the stock because there is nowhere for it. We just don't. We'd be better off insulating the walls with fibres. You know, it just can't work. You know, because that graph will always deny you that last little bit. Yeah. Now, the thing about it is that all of the measures, the education, you know, the insulation, the getting the systems to work, and lastly, you know, putting all the bling on it it's all good stuff in themselves. Put them all together and say this is a standard. We're on the road to nowhere. Yeah. Now, just for example, on 55 Wolvercote Road, the double glazing that we took out was only 4 years old. It had been installed 4 years ago at a cost of £9,000. But because we were going for Passivhaus, we took it all out. And we spent £29,000 putting, you know, triple glazing in, you know. And just a note here on Passivhaus compliant products, yeah. This is all run, it must be run by the mafia, because it's the closest that I've ever got to extortion, right? £4,500 for a front door. I mean, do me a favour, that's 10 times. Well, when Mark said I was getting a great deal, but £1,800 for a garage door, I nearly fainted. But £4,500 for a front door, and it doesn't work. You just seen the evidence. It doesn't really work, you know. The people who've moved into this house, I mean, they couldn't let it. That was the other thing. They had about umpteen viewings, couldn't flip it, let it. But the people who've moved in got a stack of kids. They're lovely people. And what do they like best of all? Is it the fabulous double glazing? Is it this brilliant door? Is it marked aerogel? You know, they like the colour. Can you believe that? Anyway, just to move on. Right. So everybody has renewable energy problems. Retrofitting is bloody difficult, right? Here's a very, very famous one. This is the wind turbine on David Cameron's house. Never worked from the day they put it up, right? You know, right? Sensibly, you know, insulation works. Put it in. That's it. So what happens next? I won't go through all of that, but this is all essentially what we're going to be, you know, doing. And you know, the whole emphasis, you know, the government's waking up. It's, you know, it's going to be about decarbonising the grid. Yeah. So we're going to build wind farms. Yeah. And then ultimately, you know, when the economic case becomes overwhelming, we're going to go back to atomic. So that's it. Case study. Blah blah blah. This is why we couldn't get it airtight. It was the original construction, but this one got picked. We were going to do another building completely, but we had to have a south-facing. We had to have a south-facing flank wall so the aerogel technology could work on it. So we couldn't even roll this out across the rest of Thamesmead because it all points in the wrong direction. But nevertheless, I mean, it was great fun. The thing about access, right, is they are Galleon's Housing Association, people who own Thamesmead. They're their long-term framework partner. Yeah. So you know, even though I went through this, you know, if you remember the meeting, oh yeah, I'm considering this. It was a done deal. It was a done deal. It was going to be accessed from day one, you know, and we negotiated the price. The price was a fair price to begin with, but it was always going to be access. And access represent the British construction industry. You know, I know Mark was terribly disappointed with the skill standards, but that's what we deal with on a day-to-day basis. Do you know what I mean? 70% of any building is wrong, you know. So, Mark's gone through all of this. It's a lot better than I can do it. So, right, this is the tree hugger in me. Yeah, this just to show that I'm not some kind of anti, you know, I'm not like George Bush or Jeremy Clarkson. Do you know what I mean? So here it is. I bought this house, right? And so I thought, well, listen, Passivhaus, yuck, right? I'm going to go for, you know, completely carbon neutral here, right? You know, so I stuck in photovoltaics. I've got the solar thermal collectors. So, and of course, it's a huge fiddle in the way the calculations work, because if you burn wood, right, it's carbon neutral. It lets off loads of carbon, but because it's like current carbon and it's not deposit carbon, it doesn't count. Yeah. So we did all of this, you know. But believe me, you know, the only way you get warm is running in and out with the wood to fill up the bloody right. So you got everything. Solar, you know, got this is great. I mean, the Gled Hill, all of that sort of stuff. You know, Anyway, we lasted about 9 months. You know, completely carbon neutral. You know, I mean, my wife was really up for this. I have to say. You know, she's, you know, but. By God, did it get cold in the winter. I mean, it just got cold, so cold in the winter. Fortunately, when we were having the works done, the plumber had said to me, you know, listen, you're going to have a gas boiler. I said, no, you know, no, I'm, you know, we're not going to have a gas boiler. So anyway, eventually I phoned him up and I said, we need the gas boiler. But I said, of course it's going to be murder. You know, we're going to have to put up floorboards. We're going to have to do it. He said, no. He said, tell you the truth, Jim. We didn't listen to you. We put 2 pipes in because we knew you were going to make this phone call. So they put a gas boiler on. Fantastic. The underfloor heating worked and everything. Yeah. The poor old, this old thing, you see, that worked a treat in the autumn and the spring. You know, because the thermal output, you know, from the wood was enough to do. Once it got really cold, you know, once the snow was on the ground, we needed, you know, state-of-the-art condensing combination boiler, whatever. Right, and so that's it at the end, right? Now, right, the payback period has reduced thanks to Mark doing the calculation. Last time he did it for me, it was 11 years. And we're on the knife edge at the moment because, strictly speaking, if we produce more electricity on the roof than we use in gas in the gas boiler, so if overall the house makes an energy contribution, then we're carbon neutral as far as I'm concerned. Yeah, I mean, I won't go through. We insulated it. We did all of that sort of stuff. You know, but essentially, I won't bore you with any more of this. I'll get sensible again. The problems with Passivhaus is one is the Passivhaus compliant products, right, are extortionately expensive. I'm just talking about cost now. Are extortionately expensive. Yeah. So you know, 3% over or whatever. You know, very, 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 very difficult to achieve, particularly when you're having to pay, you know, $4,500 for a compliant front door, and it was the only door we could buy. There was no other door. The other thing is the testing. Yeah, when we had a revision of the building regulations, yeah, and the idea was that we were going to test new builds for their acoustic performance afterwards. Yeah. So once it was built, a man had come along with, I don't know if you've ever seen, he bounced a ball on the floor. It's the stupidest thing you've ever seen. A bloke with a tennis ball bouncing up and down, and a bloke underneath with a bloody mic. It's stupid. But anyway, that's how they do it. And this was going to be rolled out for us. All of the volume house builders, of course, stood up as one and said, we can't have this because the risk of failure was too great. So they dreamed up this idea of robust details. I'm sure you're all very familiar with robust details with regard to acoustics. Well, we're going to have to do something like this for Passivhaus because the risks of failing the test will put people off. Because anyone who's been through this will say no, because it's not worth spending all the money only to fail at the last hurdle. You know, so we won't do it. You know, we'll talk about something else. So a set of robust Passivhaus details would have to be adopted because the one thing that's going to stop Passivhaus being generally adopted in refurb, you know, and the other thing is by 2070, I think you said 70%. You're joking. We're not going to knock down any more buildings. You know, all of the buildings we've got now, we will still have in 2070, and we're adding to the stock at something like 0.25%. Per annum at the moment. I mean, we built 63,000 houses last year. I mean, it's just unbelievable. Where are we going to put all the people? Nobody knows, right? So the thing is that if we are going to tackle the problem and why it's been laid on housing, I don't know. But if we're going to save the world and save the polar bears, right, by reducing the carbon footprint of the housing stock, which is suddenly like the most urgent issue ever. We're not going to do it through Passivhaus. There's going to be a load of other measures that we're going to have to adopt. Decarbonising the grid is key to them. Which means however many wind farms we build, it means atomic. Passivhaus has a role to play. Carbon-free living has a role to play. It all has a role to play. But the emphasis will move away from refurb. It's had its day in decent homes, As society now becomes poorer, the standards that people live in will be allowed to slip, and it will be some time before the pendulum swings back, and Passive House may then have its time. But I'll shut up on that. Thank you. Thank you.
Thank you, Jim. Next speaker is Tim Mander, who probably also needs little introduction. We've worked with Tim on many projects. Tim's a structural engineer and is a founding partner of Integral Engineering Design, which he set up in 1999. I'm going to quote from his website, which Tim says he firmly believes that good architecture and good engineering go hand in hand and need to be fully integrated to deliver high quality buildings cost effectively. So that says a lot about the way Tim works. He's been at the forefront of sustainable design thinking for over 20 years. He's involved in teaching and research at Bath University and also the BRE. So, Tim, over to you.
Thank you, Russell. Thanks. Actually, the theme this evening is new build. Refurb. But I just wanted to say, as an engineer, as we go about working with lots of different architects, that some of the issues that we're facing and where we see different architects coming from, and I'm not saying I've got the answers here, I'm just saying that this is some of the things that we're seeing as a practitioner working with architects who are persevering for Passive House. This was a slide I saw the other day, and I was just quite surprised that between a third and 50% of the CO2 emissions that we generate are down to buildings. I was quite surprised at the scale of that, and so I just wanted to start with that. I think the other thing that I want to talk about later is we need to be, Passive House is wonderful in its own right, but we need to be looking at this bigger picture of the life cycle carbon analysis. And this is quite an obvious slide, but I think it just does reiterate the fact that if we're going to address these buildings, we've actually got to start from the concept stage of a design process. I find that it's quite frustrating. We kind of go into meetings and we all eventually get appointed when we've done a bit of work and one thing or another, and then we think about bere, how are we going to do it? We're going to go down lead, or we're going to do Passive House, and before you know it, we're quite a long way down the design process, and we've made very, very key decisions already, and actually we need that input right at day one, I think, if we are going to start to address these lower carbon buildings. So it's a very key feature. It's quite obvious, but it does need to be stated. This is the specification of Passive House, which I'm sure you're all fully aware of, but the beauty of Passive House is as a performance specification, as opposed to a BREEAM, which is more of a kind of sustainability assessment. So it could be argued that this is great as designers. We've got about 3 things we've got to comply with, and so this does free us up, and it's quite a nice holistic way of looking at life. I just wanted to say a little bit about the key issues that are facing us, and no doubt you're all aware of those. I don't need to bring those out, as Jim says. I'm sure you're all aware and alert in all this, but I just kind of look back on this building actually that we did about 10 years ago now, and won a few awards and one thing or other, but actually would we be doing this again now with what we know about Passive House? And obviously we're all fully aware of the kind of steel and concrete cold bridging, but kind of 10 years ago we thought, well, actually timber is still okay to fly from inside to outside a building. So potentially would we do this now? Potentially we might think twice about it. But as we go about detailing our buildings, which I think is the key to Passive House, is how it's the connection between the kind of inner skin and the outer cladding, which is that insulated zone, and how we physically kind of connect through that zone is becoming quite key. And this is just a roofing system. It can also be used as a walling system, but here you see a very minimal connection between the inside and the out, and these are kind of insulated kind of I-joist systems that very much we're seeing a lot of people use in the with Passive House itself. And there's quite an often debate about how we go about detailing these buildings, and particularly whereas in the past we see developers kind of put in kind of columns within wall zones, and we can't do that now. We're trying to kind of create this kind of quilt running around the building itself. And this is the thermal imaging from the Bauhaus at the University of Bath, which is the image I showed you earlier. And this is where I can be persuaded either way, because actually there's a blatant cold bridge through here. We've got a solid timber floor. This is a CLT floor here, just coming right through and to the external cladding here. And it's not showing any real signs of thermal bridging at that location. So I think there's quite a debate about this, and we were pleasantly surprised because I'm also director of ModCell, who've developed the Bauhaus system. But what we're starting to see more and more with architects as we go down this passive house is we've come up with this kind of fabulously insulated roofs and wall construction, but actually what do we do with the foundations here? Obviously in retrofit, it was interesting the point you were making about the retrofit itself and how you can put that obviously on existing slabs, but actually we're finding that architects are starting to get concerned about cold bridging from the ground itself into the structure, and so we're finding with a number of kind of passive house buildings that we're starting to float the whole building itself on rigid insulation. So we're actually putting a lot of these buildings on raft foundations these days, and so we're trying to minimise the thermal bridge itself through the foundations. But I just wanted to come back to another point on this, which I think is probably more pertinent than cold bridging, and this is very much down to how our buildings kind of move and settle down with time. And for those that are built in timber buildings, that timber is an absolutely fabulous material, and we've got a lot in timber, but you need to understand how timber performs. And basically timber will shrink by 0.24% across the grain, and it's got very little shrinkage along the grain. Now that shrinkage is for 1 percentage change in moisture content. Typically timber that's delivered to the UK is coming in at about 12, 13, 14% moisture content as a kind of glulam structure, and then we put it into a building and we whack the heating on, and if we go back to this detail here, then what we find is actually inside this is kind of heating up and drying out nicely, and outside it's drying a little bit, but actually what's happening is that this timber is in fact shrinking. On that depth of timber you could be looking to kind of shrinkages of 3 to 4 millimetres, and this all comes back to the tapes and the detailing, but we've got to understand how these buildings settle down itself. What was interesting about the Bauhaus at Bath is that we tested this building when it was first completed, and the air tightness was less than 1. We then went back about 18 months later and it was about 1.8. And that isn't solely down to the movement in the timber. There's also kind of various seals on the door start to get brittle, and bits of rubbish get in and one thing or another. So if what I'd say is that these buildings stand up with very good air tightness, well hopefully they are if they're kind of correctly detailed and inspected and all the rest of it, but kind of post-occupancy, when the building starts to settle down, and yes, we could argue it's potentially more of an issue with timber buildings, but I think this does happen on other forms of construction. I just want to say a little bit about this, which I think kind of picks up on Jim's point. This is the hemp pod at the University of Bath, and this is a demonstration product. This is triple glaze. This is using hemp that's sprayed in between the walls. And what was interesting about this is achieving air tightness of less than 0.6, all very, very good, but there's no mechanical or ventilation heat recovery system within here, so you kind of, this is only a little small room in here, and you get in here and you start shutting the doors and the CO2 levels go up very, very quickly indeed. And the other interesting aspects about it is that because they went in there and bought lots of IKEA furniture and put it in and one thing and another, but before you know it, it's got a very poor air quality because of the high VOCs that are being generated by the furniture itself. And somebody might argue, well actually why is this relevant? Because actually surely you've got an MVHR system, but picking up on Jim's point, I think you'll find a lot of these people turn them off, and there's been a lot of post-occupancy evaluations where significant people are turning these off because they don't like the noise and they don't understand them, and then suddenly we've got these kind of superly sealed buildings with no ventilation in, and what's this going to do to the occupants? So it is always that post-occupancy that, and Jim's actually spot on with that, and I think you're absolutely right that it's the occupants that can deliver that. And so that's kind of my experience of Passivhaus. But what I wanted to also talk about is that one of the great things of Passivhaus and BREEAM and sustainability and one thing or another, that we can be very good at getting down this operational energy and or the operational carbon, and we can start seeing some renewables on, and we can get down to these zero carbon buildings. But this is potentially only half the story, because actually as we go ahead with kind of new buildings, obviously they've got significant amounts of embodied carbon itself, and if we really do need to start looking at more of the holistic, the whole picture, as opposed to just kind of operational energy, because there are a number of Passivhaus buildings that are built out of concrete. They're superly airtight and one thing or another, but if you actually do the life cycle analysis on it, on the carbon, you really think, is this the right thing to be doing? And obviously it was interesting in the kind of previous speakers that actually one of the best things that all these retrofits have done is that actually we haven't expended much in the way of embodied carbon. It's been very minimal. So in fact, I actually think this whole retrofitting is a fabulous thing to be doing, and it's kind of missing a trick in a way, because it's the ultimate sustainable thing to do. But if we look at operational the embodied on buildings, then why hasn't this been potentially thought about too much fast? Because potentially our buildings have been big kind of gas guzzling buildings, and embodied carbon has been very little in relation to the operational carbon of the building itself. And the latest research is starting, is this coming on there, to show that actually we're getting kind of parity now between operational carbon and embodied carbon. And I saw a chart the other day which is potentially saying that by 2019 75% of the carbon that's generated in the life cycle analysis of a building will in fact be due to embodied. And this is as a result, which is all great news, of kind of Passivhaus and becoming more sustainable and cutting down this operational carbon, and suddenly this embodied all becomes far more important. And this to me is where I think we're struggling as designers, that we're not really starting to address this embodied carbon itself. And as engineers, that with a typical kind of 50-50 split between operational and embodied, that the foundations, the floor structure, the roof and the external walls make up 25% of the whole life cycle carbon cost. And nobody really comes to me in a meeting and says, you know, kind of how are we going to get the carbon down and one thing or another. These decisions get made very early on, or we're going to go for a concrete structure or whatever. And but yet we then focus enormously on kind of Passivhaus detailing, and I start to think we're actually missing the point at times. For those that do want to get into this, I just want to say very briefly about what we're trying to do to address this. That for those that haven't got involved in embodied carbon, the data which is generally being recognised, the inventory of carbon and energy out of the University of Bath seems to be recognised now as these kind of data for making assessments on embodied carbon. We have got a package now that we've developed that we bolt on to Revit, and once you start developing these Revit models, the beauty is they're giving you all the quantities, and you can easily then put these into the data from Bath University, and we can then carry out, we then start to form a database within the office about where we're stacking up with comparisons of carbon within the structure itself, and then there's obviously the added benefit of sequestration within timber, which is quite a hot topic, but I think you actually should be taking it into account. And I think what I want to say, come back to this graph, is that what's so fabulous about this is making the point I was making earlier, that actually with all this retrofit, the beauty is that we're not actually doing all this. Okay, we've got the external walls and the roof, and there's a little bit here, but generally retrofit is actually, when we start the whole life cycle carbon again, it's obviously a thing to be doing and stacking up, and giving a structure a new life is obviously the thing to do. So where do I stand on Passivhaus? I think it's an excellent performance-based specification. I think The rigour in the detailing is good up to a degree, a level, and I think they're quite ambitious energy targets. I thought it was a really interesting graph that Jim had about cost v targets, and I think to actually get that top end of the curve, I think we are throwing lots of money at it, and actually if we were to achieve 30 kilowatt hours a square metre, I think we would be doing pretty well actually. And so I think my philosophy is that we should have the aspiration of Passivhaus, we should be going in the direction of Passivhaus, but I question whether we should be triple glazing all of our buildings, and I agree with Jim, chucking, that is obscene actually, throwing stuff in the skip and spending 27 grand on is just wrong. And in fact, that it would be interesting to have done that carbon analysis on all that, because I think we would probably be quite surprised actually. But the other thing that I think would be quite interesting to debate after this is whether Passivhaus is applicable to educational and commercial buildings. I question the very kind of different densities of people within there and whether that's right. And finally, I think do start considering this embodied carbon. We have got to be seeing the bigger picture than just looking at kind of operational energy. So, and finally, which I think what today is about, is that actually we're all very, very good at this and we all think we know the answers, but actually it's great to see the work of Martin. Are these buildings actually stacking up and performing? Are we achieving these air tightnesses and one thing like that? I think that we have some enormous challenges together as an industry, and I think that today, this kind of forum here and how we go forward, we have to be very honest with one another and say what has and has not worked. But I say I think we have got some enormous challenges ahead, and we need to be honest and frank about what has and has not worked. And that's essentially what I want to say.
Thank you, Tim. I'm going to ask the panel of speakers if they wouldn't mind just filling in their chairs already. For fascinating and very different approaches to Passivhaus design. And, I'm going to start just by throwing it open. Who wants to start? Justin.
Firstly, I thought they were just like 10-minute talks, so hence Maiia was just concentrating on the, on the subject of cost rather than the whole, all these other topics, which I'm sorry, Jim, but amusing and rabble-rousing as it was, really frankly a load of complete and utter rubbish being spoken, I'm afraid, from top. And I can go through the points.
Far away.
All right. I mean,
I love a bit of creative tension.
Firstly, you start by don't start by talking about. I think we're talking about a £600,000 building which didn't require Passivhaus, and start comparing that with Passivhouses. If you're doing a retrofit, if you're looking at retrofit for future, look at 2 buildings built for a sixth of that money and have been rigorously tested and analysed by the head of the Energy Institute at UCL, and are found to be head and shoulders above all the other retrofit for the future buildings that they've looked at, and they've done to the Passivhaus approach.
Just on the cost spec, the actual capital cost of all the measures was 80 grand on that project. So
right.
the rest to get up to 330 was all kind of
bed spaces.
Okay, so
yeah.
but I mean, going through. I mean, firstly, there's so many things that go through. First, the point about the door, for example. When I first saw the door, the aerogel door, I saw light coming underneath it. So I'm not surprised there was quite a lot of heat loss, visible. Okay, sorry, I was saying firstly the Passivhaus door, when I saw the aerogel door, I saw the first photograph of it, I saw light coming underneath it. So you can't compare the cost of that with a door that has double seals and is airtight. Okay, that's number one. Number two is, if you're looking at thermal imaging, we need to know what the internal temperatures are. Presumably you're not heating the plant room.
Yeah, well...
So if the plant room is cooler than the main house, then of course it's going to be,
Well,
there's going to be a lot less heat loss through. But
well,
anyway,
those
U values
tests
are very
conducted, we also measured the in-situ U value of the door.
Yeah.
We had a heater in
yeah,
the
well,
plant
U values are very easy, and of course you can throw
So we
them
were
in. You can-
using the plant room is the point I wanted to make there.
but we need to see the temperature comparisons. But anyway, in a way, that's slightly.
Read my thesis on that one.
But
Yeah, read my thesis.
the U values are one thing, but you lose.
No,
you lose half the heat through the
absolutely.
drops.
That's where the downfall of the product was,
So-
just the air tightness.
And then it's also what goes into the cost of the door. It's the multi-point locking that keeps the keeps the door square on the seals. There's no point in having a single latch because the door will warp and air will come in around it, and you're wasting you're wasting your money spending it on a load of aerogel if you haven't dealt with the latching and the seals and the adjustable hinges and all those things. So I can go through, and maybe I will go through a whole load of things.
Well,
but
maybe we can chat after.
no, but the point is, I really don't need to be discussing these things, really, because you just look at the results. We've moved beyond this kind of, silly talk about returns and so on, comparing, doing speed to build Bordas. Why, in fact, in results, are ordinary building regulation buildings in BISRA tests recently on academies using between 2 and 5 times as much energy as designed. Why is that happening? And why is every single passive house that's being analysed under the Technology Strategy Board building performance evaluation, why is every single one using less energy than designed? Now, as soon as you start comparing a building which has a much looser attempt to save energy in the first place, and even so is using 2 to 5 times as much energy, you're talking about scores of 10, 15, 20 times as much energy in the ordinary building being used than in the passive house. You've got to start making proper comparisons. I've asked Bill Bordas why, in his view, and hopefully most people here know who Bill Bordas is, why in his view are those buildings using 2 to 5 times as much energy? One of the key things is airtightness. Elizabeth Fry building, East Anglia University, built in 1995, not to passive house standard, to a very good airtight result, 1 air change, has achieved far, far better energy saving results over years than any single university building since. And a lot of that is due to the airtightness. And why is it due to the airtightness? Well, Bill Bordas will explain. It's that in a passive house, if you've got all your leakage that causes it to go from completely 0 down to 0.6, if you concentrate it all in one room, you won't feel uncomfortable. But if you have got an airtightness of 5 or something, or 3 or 5 or 10 as building regs, and you just have a small percentage of those leaks in one room, you'll feel the cold draft in the winter, and you'll go and turn the thermostat off. And that's why the occupant in ordinary buildings is really a problem, as you've described. He or she is turning the thermostat up. But don't blame the occupant. Blame the design method. If the design method doesn't work for the occupant, then replace the design method. Our Camden Passive House, we just 2 days ago had the UCL results, first year monitoring results, again achieving better than performance, than design intention. The inhabitant there isn't interested in low energy at all. She's been given the place by her father.
I mean,
she goes out to work in the morning on a winter's day, leaves the blinds down, and gets no solar gain, and yet it's still performing better.
Before we move on to another point, just in our company, we worked on a project for design 26 low energy houses in Suffolk, and we had a research engineer looking specifically at the total gas and electricity consumption of each individual house and comparing the difference because of the users. And basically what he found was that the variance in energy consumption is between kind of up to 5 to 10 times difference between the lowest and the highest consumer. So it's not all to do with design detailing. It's ultimately about the
shape of the
users
graph
and their education.
The shape of the graph is down to design detailing. Yes, there have been European
Sorry, is
performance.
this a question or?
No, I'm telling you.
Oh, you're right.
The shape of the graph is hang on, let's like that. Okay. That, if you've got lots and lots of buildings, identical flats, there will be in any design methodology there'll be the lowest user down here, who's perhaps eco-warrior, and there'll be the highest user here, perhaps disabled, elderly, can't move around, needs extra heat, and in between, we'll get an average. Now the shape of that curve in a normal building regulations building is the same shape, but the steepness of the graph is completely different. So we're comparing, in a normal building, this actually tends to be a bit steeper than that, with a passive house, which is right down here, a much shallower curve. So the difference between the highest user and the lowest user is much less, and the highest user in the 15 kilowatt, if we're taking that figure of the heat load, the highest user in the 15 kilowatt kilowatt hours per metre square per annum can never use more than the lowest eco-warrior in the 30 kilowatt hours.
It's the heating though, right?
So
the heating.
Yes, and that's 40% of the total energy.
Translate to electricity with it, because you.
No, that's right. No, but the largest
total consumption wouldn't quite follow that path, is what I'm getting at.
No, that's right.
Yeah.
Not the total, but the
heating consumption.
Yes, but the heating is the majority. Is the largest thing.
Well, it's the majority of what we've got now. But if we do have passive houses, then electricity use is going to far outweigh consumption. Yes.
The electricity consumption won't go up.
Well, it might do. We don't know how technology is going to develop. We don't know what products everybody's going to have in their houses consuming electricity in 20 years' time.
Okay. Well, I mean, the results, we don't need to just talk about hypotheticals. The results of the
But realistically,
the electricity consumption is staying the same or going slightly down in comparison to building regulations. And a lot of that is to do with.
I mean, I'm talking about unregulated energy, so what's not covered by the building regs. Building regs isn't a. It's not a prediction. Building regs, it's just a compliance method. So there is still that discrepancy between what we predict in building regs and then what actually happens. In terms of the small power loads, I mean, there's a huge story that's not being told.
Well, in passive house, in a non-domestic passive house, for instance, every computer needs to be listed. Its make, it's how many kilowatt, what its energy consumption is, how long it'll be on during the day. Is the user standing or sitting? Because all we're talking about is a very scientific method of measuring all the energy out of the building, all the energy in. That's all it is, and it's just being scientific about it. And I'm just rattling off a few of the completely unscientific, opposed, reasons for not doing passive house that have been stated, which are frankly, just absurd, and they don't stand up to scrutiny of the scientists who are doing really good work investigating the difference. And I attended a talk at UCL a year or two ago by some researchers there, and one of the chaps had done research on EST light retrofits, sort of cavity wall insulation, lofts and so on. They were all supposed to have achieved, and this was in Ben Crox's, I think in his group, what they calculated was that the buildings would achieve 15% energy saving, but they were achieving nothing. Why is that? Well, it's obvious. The people who are living in 17 degrees, 17 degrees, 16, 17 degrees in the winter, are obviously going to take that extra and go up to something comfortable. And what Rob Lowe is concluding, head of the Energy Institute in UCL, after the Retrofit for Future project, looking at all the projects that he's been given to look at, is that we can aim for 80%. When we get that, that extra comfort which people are entitled to, then we'll get 50%. And that's if we do a really deep energy retrofit. So let's not, try and kid ourselves that we can do, a little bit and get a long way. The only way is to do it really rigorously. If we screw up on the air tightness, someone will turn the thermostat up. As simple as that. And we won't achieve the design targets. And that's the fact. That's what's happening all the time. 2 to 5 times, repeatedly 2 to 5 times the energy consumption in normal so-called low energy buildings.
Yeah,
I'll just come back on that. I mean, you may think everything I said is rubbish, and I'm sorry that you do. All I think I was talking about, and I'm certainly not a scientist. Fortunately, I had a very accomplished engineer on the project. We had a very well-established firm of architects on the project who was so committed to Passivhaus, they were off the Richter scale. But this wasn't done in a university. It wasn't done in a Revit. It wasn't done. This was done in the toughest place in London. Believe me, the family that have moved in there, God's honest truth, and strike me down if I'm wrong, but I doubt if any of them can read or write. They've got 6 kids. I think the eldest is probably 9. The youngest is a baby. The idea that we've put them into some kind of technological miracle that will change. They chose that building because they liked the bright colour. I know Angus Brown is thrilled about that, the architect. But honestly, what I said wasn't rubbish. I'm not a Passivhaus authority. I don't claim to be. I've just come along relating my experience of trying and failing to achieve Passivhaus standards on a building that, if we're going to roll this out, we're going to have to make it work on buildings like this, and just related the reasons why it failed and my thinking on those reasons. You may say I'm wrong, but it's not rubbish. It's a valid contribution.
Thank you, Jim. I'd like to get some questions off the floor, please. And we have the gentleman in the back there.
Yeah, my original point's kind of moved on really, because it was to do with the talk about unregulated energy. In fact, Passivhaus, unlike Building Regs, does account for regulated energy, which Justin's kind of explained. And the first Passivhaus that was built in the UK at Gynolfyn Hwthgen in Machynlleth did actually meet all its regulated and exceed all its regulated energy targets, as well as its regulated energy targets, all delivered for less than £1,800 a square metre. It's all perfectly doable. All those arguments are wrong. And just to relate back, it's all about the designers. What you guys made a fundamental mistake, in my opinion, on 55 Water Code, which I know quite well, because you tried to get airtightness by taping up the insides and not thinking about all those party wall junctions. If you thought about it perhaps as a parge coat on the outside, dealing only with the penetrations that you had to deal with that went from inside to outside, you might have had more of a fighting chance of getting the airtightness that you need for a Passivhaus. And to say the client's been put off is wrong, as you should know, Jim, because your company is involved in the next bigger scale development on that housing estate, which is going for EnerPHit standards, but albeit in a completely different way. So I think there's a lot of smoke and mirrors being talked about here, probably just to generate a debate, but it is a very viable standard to aim for. There are going to be lots of old buildings where we can't get anywhere near Passivhaus because you don't have the flexibility to adapt your solar gains, etc., etc. But I strongly believe it has to be part of what we aspire to, and it's in a lot of our 60s buildings, a massive amount of our stock. It's perfectly achievable to get there, and as we're showing on the very next building on the Thamesmead Estate. And I'm also an RBA Sustainable Futures Group committee member with Justin, and I have to say I've been pretty disappointed with the level of debate and understanding about Passivhaus here tonight. And clearly we, as the RBA, have got a hell of a lot to do to educate our members on the reality.
Just sorry on that point. The presentation that we gave today was basically telling you the story of when we started back in 2008 and the decisions we made back then. Those kind of lessons learned that I pulled through at the very end. That's where I would probably start now. I think, all right, there are all the things that I did wrong first time around. Now when I'm doing it, I'm definitely going to use that as a baseline to go forward. And I mean, in terms of the debate here tonight, I think it's great personally. Just going back to the unregulated energy stuff, I think in non-domestic it's a lot easier to kind of have control over what small power plug loads electricity use is going to be in, but in a domestic setting it's a little bit more tricky. I think obviously you've got your white goods and your appliances, but then after that it's a lot more uncontrollable, I think. So Passive House can't control everything as to what the users are going to be doing in their houses for the next 30 years. And just on the point about specifically the detailing on our project, FBM Architects, through their kind of Revit model, did treat the party wall and create a house which on paper would theoretically be airtight and have no thermal bridges. However, our main kind of issue was just the fact that the contractors just didn't really have the kind of integrity to get it to be honest with us when they were having challenges.
Sorry, let's not blame the contractors. We've worked with, on most of our projects with the contractor who's never done it before. And it's down to the design team, down to the professionals to train the contractors in all these little plots. I mean, don't blame the contractor. They will do a wonderful job if they are inspired to do it. You need to inspire them.
In our particular project, though, I mean, it was the case of saying to them, have you put tapes around the perimeter of the door and the glazing? And they're like, yes, of course we have. So we're saying, okay, let's pull out the external insulation, do an abortive test and actually have a look at it. And the tapes weren't there. The boiler fluid didn't have a sleeve. Yeah. And the site manager was...
It's the process that's wrong. There's a problem in the process.
The site manager just wasn't being honest with us, I don't think. And as a result, we had a lot of issues.
I think it's also worth saying that the Galleons did employ a very notable Passive House consultant who was Dutch, who was completely on board and signed off on all of the designs. So it wasn't as if the client did everything they possibly could to deliver their objective. Just quickly on that other building that you referred to, we've got loads of cost plans that said it is cheaper, financially, not from a carbon point of view, to knock it down and build new, but it's politically unacceptable. So that's the reason that we're pursuing a refurb to Passive House standards on that particular building.
I just wanted to add to the point is if you are doing a refurb anyway, the building regulation standards are actually quite high nowadays. So that's where sort of in my presentation, looking at the difference, you find that 3% is actually very little, considering the amount of energy you actually save. I mean,
it's not hard.
I wanted to touch on payback periods.
Stringent on the airtight Building Regs requirements at the moment, which is ultimately the main kind of failing as to why we didn't achieve Passive House. Really.
And the Passive House compliant products.
No, they don't slay. You can build. No, that's a wrong statement again. You don't need to build a Passive House with a single Passive House compliant product. If you're talking about past tests, it helps. It gives you reassurance. But there's no mafia involved, and that is a highly, really nice point. Yeah, but it's the person
Dutch
you met,
mafia.
you wouldn't say that. So if you met Wolfgang Feiss, who's a university professor who has made this his life, who still lives in the same house, little block of little flat that he built in 1995. He's not in it for money. The software costs £100. He could, he's not like, AutoCAD and Bentley systems and so on. It's not trying to make money. It's not about money, honestly. So don't please anyone think that.
Any more questions?
The most expensive inter-norm door in the catalogue. It's no wonder it costs a fortune. There's lots more out there that are more affordable.
I'm Ben Croxford from UCL. I thought I'd say a few words, if I may. Justin comes in and speaks on our course anyway, so I know him pretty well and I know what sort of buildings he's been involved with. And I'd like to just say a few words about Jim's presentation as well, which I really liked, really enjoyed. I was really interested in.
He said some really good stuff.
And the others as well. I just thought I'd kind of take it back a little bit to the is Passive House sustainable question that's sitting above all of your heads. And I think Justin's certainly shown that it's if it's done well, it works. And I think that's the sort of key bit. And perhaps Jim was showing that, or reminding us that this is a new kind of development for the UK to try and do this refurb. And it's difficult for most construction teams, if you like, or design and construction teams. I've been involved with one with Thorne Architects in Haringey, and we've been looking at that in really high level of detail to see which bits work, which bits don't work, why they do work and why they don't. And there are problems, it's difficult, we don't necessarily know how to do it, and certainly Justin's really committed and has been involved probably really intensively with the contractors to make sure that they did it right. And certainly in the house that we were looking at, towards the end, it was packed full of contractors, so there were maybe 13 or 14 people in the house doing stuff. It'd be very difficult to make sure each of them did it right all the time and keep an eye on all of them all of the time. And I think that maybe is the bigger question of which bits work in reality when you start rolling it out to big numbers of houses, which is what is going to have to happen. And making sure that works is tricky stuff. I like this bit of the wall of looking at the wall of this end terrace house. I mean, you're looking at it and I'm thinking the bit that worked very well on the Haringey house was this external insulation, which they must have done in 2 or 3 days, which was putting polystyrene on the house we were looking at, big chunks of polystyrene rendering over the top of it, and it was done really quickly. And that is probably quite cheap to do and works quite well. And in that house you've got quite an expensive solution. And it was probably quite easy to do in terms of access to that particular wall.
Yeah, I mean, just from the cost of it, the kind of installed cost of that collector we built was only 1,500 quid actually. And then controls to kind of work the dampers in the plant room there, probably we had three damper plates, all 200 quid each. So I mean, it wasn't actually a massively expensive technology.
Sort of continuing, if I might, the TSB process was to try and upskill teams of contractors around the country and try and get all of them to be able to do a good job and to learn what worked and what didn't and how to get a few people learning how to do it, and they teach a few more and they teach a few more, and this would spread out. I think that's a good process, but I feel it's early days still. I think maybe that's something to take away as well. Maybe I'll shut up for now.
On that point of the how do we upscale it, it is a really, really important point. And I know we are working hard to try and prove that in the UK, where people were saying it wouldn't work a few years ago, that it does work. We're now looking at how to scale that up. And one of the most interesting projects for me in trying to address that is with a big North Country housing. It's a council housing association, effectively, and with 400 in-house, full-time tradespeople, and that's the key to it. 200 managers and 400 tradespeople. So we are, and they're normally involved in maintenance, and now they're going to be gradually, we'll get an A team, what I call the super advanced skills team, which they like, the SAS team, that will be drawn out, the best people will be drawn out to spearhead building the new houses, taking over from all the from the contractors and the subcontractors that normally do the work. And what the key point here is investment in skills. No longer can contractors just hire and fire subcontractors. No longer can contractors be virtual companies with 3 or 4 managers and a QS who are just trying to strip as much money as possible out of the project. It's got to be contractors who are, we need to, and we have the power within the professions to help these kind of old-fashioned contractors who are, again, going to be valued, I think. They bring in the trades, the apprentices, they're training them right the way through, picking up the skills from us and putting them back again into the next project and doing it better and better and better. That's essential. Just on the point of Tim's on the embodied energy, which I think is a very good point. We're working with Sturgis Carbon Profiling. They were involved in our BRE Passivhaus competition winning prototypes, which are yet to be built. And we're aiming to make those 0-0 carbon. So over a 60-year period, you're absolutely right, we should be going, ideally, thinking about embodied energy, which is why we're so interested in the timber frame. We are doing non-timber frame concrete as well, but my real passion, long term, has got to be that we move in the direction of timber. And if we do that, and if we think of the problems of like plasterboard, which gets ripped off every 30 years and gets put into a skip, and then no one knows what to do with it. It's a hazardous waste. If instead we think about removable panels that can be taken down every 30 years to redo the electrics and mechanicals and put back. I mean, Alvar Aalto did this beautifully. When you think of those wall panels with little vertical strips, all that is cover piece over panels that can be removed and put back. If we can do that and do it beautifully as Alvar Aalto could do it, then over 60 years with minimum outgoings of energy, but with reaping because of very low energy use, reaping the little bit of profit each year, energy profit from PV and solar thermal and renewables generally, then we can pay back all that embodied energy at the end of 60 years. And I think that's the nirvana that we should be trying to go for, and do both.
I mean,
I think
just on the Thamesmead side, when those houses were originally built, they were kind of these balanced system walls, and they had all the kind of the electrics and the pipework all embedded in them. But nowadays it's just you can't work with any of it. So they had that idea like 40 years ago, but in reality it hasn't worked. For the Thamesmead side, it hasn't worked.
Everything we talk about today, yeah.
Just on the embodied energy stuff, I've used the IC stuff quite a lot actually. I guess the only important thing to note is that it only really deals with the kind of cradle to factory gate impact. So for something like Passivhaus, it's probably quite important to think about the transport impacts as well.
Yeah, absolutely.
It's a whole hornet's nest when you get into it, transportation and cradle to grave and a whole lot. And but I think we, as designers, need to potentially have carbon consultants on board at the very early stage of a project, advising us on kind of operation on carbon. And I think that maybe carbon's going to be the new currency, and we're going to have to be arguing against carbon consultants and not just QSs and all the rest of it. I mean, I think this could be.
I'll reinvent myself.
But we have got to start thinking in that way, I think.
It's getting late. And one more question, and then I'll draw the evening to a close.
Do you think whether Passivhaus is sustainable is also a function of the external climate? Because it's all very well if you're in say Norway, it's great to have Passivhaus, but if you're in the west coast of America, say, where it's about 20 degrees all year, is it actually sustainable to have Passivhaus?
Yeah. Within the Passivhaus planning package, you have weather data, which is is provided all around the world. And if you need a particular location, it can be very quick and very cheaply calculated by the Passivhaus Institute. And then the methodologies. This year's Passivhaus conference it's a question people have been asking a lot. And this year's, firstly, some years ago, Jürgen Schneiders did research on Passivhaus in the Mediterranean climates and showed how it could work. It's a lot cheaper because there's a lot less to do, but you can actually reduce the energy consumption to the same level. And this year there was Passivhaus in southern China. The new Austrian embassy in Jakarta is Passivhaus, and that you would think there's a cooling load. Well, there is a cooling load requirement, but as long as the cooling load is no greater than the heating load would be in a cold climate, then it's still a Passivhaus. The Passivhaus is reducing the energy consumption, whether it's cooling or heating.
But if there's no cooling or heating needed?
No, well then, if you're in an ideal climate, then it may be, and I think that was covered again, you might remember, I think that was again covered. There are a few locations, I think it was Rio or somewhere,
just they're subtropical. They're kind of like you said. If you live there, then just carry on living there.
Yeah.
What they they were saying is, you know, we shouldn't base our, we need a methodology which is able to adapt to, you know, the entire world, and actually it's quite nice to be able to use exactly the same thing in England, in Indonesia, everywhere, and all you're doing is changing one data set, and it's just, so yeah, you're completely right, but only in those few isolated instances.
Which brings me on to the point that, so if it varies with location, surely it varies with season.
Varies with season.
By season.
So how do you deal with the mid-seasons when you don't?
Well, the same the way you deal in a normal house. You don't put the heating on if you don't require it. So you open your windows to purge, you know, at night time on the summer month.
Again,
but if you have a really sealed building, you have a lot of heat gains inside. Is that opening the? So you try.
If you open the windows, it's not sealed any longer. So that's what you do. If you open the windows, it's not sealed any longer. So in the summer, you open the windows.
Huge amount of heat gains. The sizes.
Well, if there was, then you've got a major problem, but there normally isn't. I mean, if you look at, I mean, again, you know, unfortunately, a lot of our work isn't funded, so it doesn't get out on, you know, published soon enough. But there is stuff on its way, and we've got masses of monitoring, summer and winter, and the two retrofit for the future houses, completely level. You know, outside you see these spikes going up to 30 degrees in the summer. Inside it's a constant temperature, summer and winter. In fact, in winter it's just slightly warmer than in the summer. And you know, it's working. You know, we can spend an awful lot of time analysing why it's working, but the fact is it's working.
Just following up from that, the issue with countries and seasons is fine, but what about decline in the UK? I don't know much about that.
Well, part of the PRE is very, very, very well. Part of the PRE competition is to look at future. Nick probably said about that because he did you know, a lot of groundwork on that. It was really highly praised by the scientists and basically, to cut a long story short, all we need to do is to create a little pocket and externally relatively outside the windows, just to take a road and part of the reason that works is because we're using ordinary sized windows. In Welsh prototypes, we've done an experiment where we've got very big windows with large house and more commercial sized windows with one house. They're both set up as house. They're both designed in slightly different ways, which just, in case anyone thinks that house is strange out, it's not. It's completely different ways. It's simply a tactical method to achieve whatever we do. One of the large area of glass is slightly, there's actually less, it costs more, it's got bigger windows, and it's got external blinds, which are Venetian windows, which cost reasonably expensive. It's actually slightly less robust than the one with the ordinary size windows. The ordinary size windows doesn't generate heat so much, so it doesn't need the blinds in this time, and in the future. Just as it's
I would just say that the beauty of the system is if you had all these questions, you need to, I'm sure that you know yourself, you know, touch playing better you can test everything. So you can say, look, all right, what happens if our building, you know, say our stream suddenly change, and I know not necessarily thought that's going to happen anymore, but you can say, all right, what happens if this happens? What happens if the climate overheats to say, you know, sort of Mander in Spain? And you can test everything. You can say, okay, well, I now know this extreme, I know that extreme. If I account for it now, then I can make a small design change which will allow you to have a robust solution in any situation. And that's what Passivhaus is saying. Yeah, you're right. You know, okay, what do? You think about it and you quantify it, and you come back with scientific answers which support your premise and those two parts.
I suspect we could go on much longer. There's more wine to be drunk, so please keep thank you very much everybody for coming. Thank you very much to our speakers.